Good evening everyone, my name is Yohana Muhammad Abdurasul. In this video we are going to discuss 12 models that I have been training where you have to choose the best one to deploy. I'm the first presenter. Our group code is SWML23. So the first model is XLM Roberta. We are going to talk about it. It's also its architecture. So this model is a multi-language model. This means it can understand text in many languages. First, the story text goes into a tokenizer. The tokenizer breaks the text into small pieces called subword tokens. Then these tokens go through an embedding layer, which gives each word a number representation. After that, the transformer encoder processes them using something called self-attention. This helps the model understand the relationship between words. Finally, the model produces a pooled representation which is sent to a classification head. This head uses softmax to output the probability of each moral category. In simple words, the model reads the story and tells us what moral lesson it contains. Here you have the Debater V3 architecture. We are going to talk about how this model works. So it is also a transformer encoder, but it has a special feature. It separates the content of a word from its position. This is called disentangle attention. Like XLM Roberta, the text is first tokenized into subwords, then it goes through stacked self-attention layers. The output is put into one single representation and passed to a classification head. The classification head then uses softmax to give us moral category probabilities. The main difference from XLM Roberta is that disentangled attention mechanisms, which can help model better understand context. Here you have the confusion matrix and results. In this slide we show the result of our two models, XLM Roberta and Debater V3. We use confusion matrix to see how well each model predicts the correct moral category. Looking at the numbers, XLM Roberta got an accuracy of 0.1667 and a micro F1 of 0.1429. Debater V3 got 0.00 for both. So XLM Roberta performed better than Debater V3 in this experiment. These are baseline results. To improve them, you need better data, labeling, and more balanced classes. Then here you have the explainable AI and hyperparameters. In this slide talks about explainable AI. The goal of it is to go beyond just accuracy numbers. We want to understand why models make certain predictions. At the global level, we use confusion matrix and F1 squares to find systematic errors. At the local level, we apply the technique called lime headlines, which words in a story influence the model's prediction the most. The results show that both models tend to collapse towards one dominant class. This is a sign of class imbalance. This analysis tells us that the accurate errors come mainly from data problems, not from the model architecture itself. On the right, you can also see the hyperparameter settings we use for both models. Things like learning rate, batch size, and number of epochs. Here you have the Llama and FLAN-T5 models. In this slide, we move to a different task, which is story generation. We train two generative models, Llama and FLAN-T5 based. The goal was to generate culturally grounded African moral narratives. We had 42 documents in total. We split them into 36 for training and 6 for validation. This split was done at the document level to avoid data leakage. Each document was then cut into smaller prompt response pairs. This gave us 288 training examples and 48 validation examples. Llama was fine-tuned as a casual language model, while FLAN-T5 was fine-tuned as a seconds-to-seconds model. We evaluated models using validation laws, Roche scores, and by manually reading the generated stories. Overall, this setup gives us a solid and reproducible baseline for African moral story generation. Here you have the architecture of the first model of the model Llama. This slide explains how Llama works. It is a decoder only transformer. This means it only generates text. It doesn't have an encoder path. The input is a prompt which includes an instruction and a story title. The tokenizer breaks this prompt into subwords units, which are then mapped to token embeddings. This embedding passes through decoder only transformer layers using max self-attention. This means the model can only look at previous words, not future ones. Then the next token prediction head generates one word at a time, step by step. The final output is a full African moral narrative passage conditions at the prompt we gave it. In simple words, it give it a title, and we give it a title and instruction, and it writes the story for us. Here you have the architecture of FLAN-T5. This is like to show it how it works. So here, this model is a seconds-to-seconds model. This means it has both an encoder and a decoder. First, the input prompt is tokenized and passed through the transformer encoder. The encoder reads and understands the instruction. Then the transformer decoder generates the output text. The decoder attends both to the encoder input and to the words it has already generated. Finally, a generation head projects the output to vocabulary tokens, giving us the final story passage. So FLAN-T5 reads the instruction first, then writes the story, which is slightly different from Llama's approach. Here you have the generative model analysis. In this slide, we analyze the result of our two generative models. We look at output quality beyond just numbers. We use validation laws and Roche scores to compare how closely the generated stories match the reference tests. We also manually inspected the generated stories to check for narrative coherence, moral consistency, and cultural grounding. The results show that Llama performed slightly better than FLAN-T5. It had lower validation loss and higher ROT-L score. You can see this in the bar chart on the right. However, we must note that generation quality is influenced not only by the model architecture but also by dataset size, prompt by design, and the limited number of cultural grounded training examples. Overall, the current limitation come mainly from data scale and training conditions, not from the models themselves. Here you have the hyperparameter table for generative models, for the two generative models. So for Llama, we use a learning rate of 2E4, a byte size of 1, and train of 2 epochs. We also use a technique called LoRa for fine tuning, which makes training faster and lighter. For FLAN-T5, we use a learning rate of 5E5, a byte size of 2, and train of 2 epochs. FLAN-T5 was fine-tuned fully without LoRa. Both models use the same max input length of 128, max target length of 192, and generation length of 140. They also use the same sampling strategy, temperature 0.8 and TOPI 0.95, which controls how creative the generated text is. These settings were carefully chosen to balance performance and available computing resources. Thank you.
Yes, hello everyone. My name is Amandi Shemati and I'm the next presenter. So I'm going to talk about long former and MBAT model. So we needed these two models so that we can understand the long African folk tales and classify their model themes. We chose long former and MBAT models because long former solves the problem of length problems. It reads the full document without cutting them off, while MBAT model solve the problem of language problem. And here we trained like 104 language so that it can transfer those knowledge across African language. So here is the architecture of the long former architecture model. The long former is a transformer encoder designed for long documents. It replaces full attention with sparse attention, allowing much longer context windows. The input is tokenized, encoded through the sparse self-attention layers, pulled and then passed to a classification head that outputs the moral category probability. Then we have the MBAT architecture. This one is a multilingual transformer encoder. It tokenizes the text into subwords, encodes them through the standard self-attention layers, then uses a classification head on the pooled representation to predict moral categories via softmax. Here we have the confusion matrix of these two models, and we see that the long former outperforms the MBAT model. So we have also the big bad robata. This one actually we used the supervised data to train this model because it is a base model used to classify African narrative, and we classify them into 13 moral categories, which we have betrayal, cooperation, courage, generosity, greed, hard work, honesty, humility, justice, kindness, respect, responsibility, and wisdom. So that when someone can click, let me say, long text, it can bring him what moral lesson did he learn from it. And here it is its architecture. Like a person input the text, then it is tokenized using a BPA in two subwords units. Like you can put there a long word, then it's going to be tokenized, then brings the moral lesson. The embedded layer maps the tokens into 768 dimensional vector, supporting up to 4,096 positions. And this is our confusion matrix of the model. We also have the GPT-2 model. Like this one is used to train the unsupervised mode, like to train the unsupervised data that we had. It trained it trained a lot of stories.
Hello everyone. Let's talk about the GPT of African moral narrative generation. For this project, the GPT is fine-tuned on a corpus of traditional African folktales and the moral narratives through unsupervised style adaptation. The model learns from 42 traditional narrative text files and generates original narrative passages that carry the cultural tone and a moral weight of the training corpus. The narratives are preprocessed by joining all the texts with their end of text the separator token, then the chunking, then the combined sequence into fixed 256 token blocks, yielding a 3 training block from the full corpus. So the base of this GPT-2 architecture is used with a standard BPE tokenizer operating as a decoder only autoregressive system that predicts one token at a time from left to right. As you can see, for the architecture of this GPT, one will have to inputted a prompt. Then for the prompt, it will be tokenized. After giving the tokens, for the tokens, we shall have the token embeddings. Then from that, we shall have the masked self-attention. Then we have the feed forward network, the residue layer norm, then the next norm prediction ahead. From this, we can have an autoregression generation whereby we shall have a feedback or an output based on what the prompt was given. The input prompt is tokenized using the BEP into a word unit. The embedding layer maps the tokens into a 768 dimension vector combining token and the position encoding. The GPT encoder rings the 12 stacked layers, each with 3 sub-component mask of attention with 12 heads, then a feed-forward network with a hidden size. That's all about the architecture for this GP2. As you can see during the training process, you can see the adaptation or the loss curve of the GP2 as it was adapting to our dataset. We can see a gradual. At first, it was a gradual decrease in the rate at which we had unmatched training losses in our GPT. But later, the losses started decreasing at a sharp curve, as you can see from the graph there. For that, when we talk about the explainable AI, the purpose of the explainable AI, the purpose of this, it is to evaluate the quality of the generated narratives beyond the training loss figure alone. Since our GPT was fine-tuned in an unsupervised setting with no moral category labels, standard classification metrics do not apply. Instead, the generated story samples are qualitatively inspected to assess whether the model had internalized excuse me, and the weight of that. Now, when we talk about the multilingual E5, which is the K-means and the Batopic models, in this project, the E5 is used to generate a semantic embeddings for the moral narratives collected from the traditional knowledge sources. I was telling you that the E5 is used to generate semantic embeddings for the moral narratives collected from the traditional knowledge sources. The model will convert each text into a dense vector representation that captures the semantic meaning across the multiple languages. These embeddings are then grouped using the K-means cluster algorithm to organize them, such that we have similar narratives based on their semantic similarities. For the bad topic, it is applied to perform topic modeling by combining transformer embeddings and clustering techniques accordingly. Together, we shall see that the methods help uncover hidden semantic structures and organize the moral narratives according to this shared culture and ethical components. When you look at the architectural structure of the E5, we shall see that the text chunks, they are converted into the E5 embeddings, which are then converted into the K-means clusters, which clusters are given labels. So the E5 is just a pre-trained embedding model that converts each narrative chunk into a semantic vector. When we say K-means, it is then trained on these vectors to discover the latent clusters of similar moral narratives without labels. Now, when you look at the bad topic, for this one, we shall see that the text chunks, they are converted into embeddings, which are converted into clusters. Now, unlike the E5, here we shall have the topic words and the topic frequencies. For the bad topic, combines the embeddings and the clustering to discover the topics, then the extracts out a representative words for each topic using the vectorizer. Now, when we continue, we shall see the E5 compared with the bad topic model. For the E5, we see that the embeddings within our map, you can clearly see that we had the aim of our training of this model was more vivid compared to the bar topic model. From this, we can see the purpose of our explainable AI, whereby we can see that the overall of this analysis indicates that the current errors, they are primarily driven by the data regime constraints rather than the architecture alone. Now, when you look at the Electra and the BAT models, for this we will see that both of them, they are transformer-based models to clarify moral narratives from African traditional knowledge sources. These models will process the folk tales by converting raw text into embeddings that capture deep linguistic and semantic relations within the narratives. For the BAT, it learns by directional representative by analyzing a full context of each word in a sentence, enabling it to understand the moral expression and the relationships between the concepts in the text. But when you look at the Electra on the other hand improves the training efficiency by using a generator discriminator framework where the model learns to distinguish between real and repressed tokens. This allows it to learn more efficiently from limited data while maintaining strong language understanding capabilities. Together, these models will provide a robust supervised learning framework for capturing complex moral patterns in the narratives, enabling accurate classification and contributing to the structured understanding of our of our ethical themes. When you talk about the architectural structure of our Electra model, the Electra is a transformer-based language model that learns by distinguishing real tokens from replaced ones using a generator. Instead of predicting masked words like BAT, it trains more efficiently by classifying each token as correct or incorrect. This makes the Electra faster and more efficient in low data settings while capturing strong conceptual representatives for tasks like text classification. Then when you look at the BAT, for the BAT model, when you look at its architecture, for it learns by understanding text in both directions, so it uses this masked language modeling to capture deep conceptual meanings, making it effective for tasks like text classification by producing rich context-aware representation of the word of our input text. When you look at our graphs, you will see the BAT model compared with the Electra, we have significant changes as the training efforts continuously increase. You will see a sharp decrease in the training efforts of the Electra, while we are having a valid in fact it is a gradual loss in the training loss of the BAT model. The explainable AI of this, we shall see that the performance limitation, again here, it is driven by data constraint rather than differences in the model architecture. The models we train, they are necessary, they provide analysis and they control layer for the project. Then together they help to clean, organize and label our data, which is essential for building a reliable training signal. Then the final step is to train our generative model on the clean and structured data. When you look at the conclusions, the conclusion is we successfully trained our models. Then the EDA was done. We had 25 visualization. Everything was done under unsupervised analysis. We had low-level learning. The project will deliver a solid technical foundation for the next 4 phases. Then the limitations we have is just the data set size, but we continue to integrate more data sets within our data set, making it robust for our models to learn more. Then when you look at the class imbalance which affects the micro level performance stability, we also have a way of handling such. Now as I reach the conclusion, that's all for the architectures of the model. We shall come when we have already deployed now the model. Thank you.